Are back, and today we are going to talk about the non-draining regime. So just to kind of follow up with this, the Stokes law is derived, just kind of an addendum to last time. So Stokes law is derived from the Navier-Stokes equation. That is way beyond the scope of this class. But again, if you're interested in kind of fluid mechanics, there's some resources that I can provide. So last time we talked about these two regimes, the non-draining regime and the freely draining regime. So first today we're going to talk about the non-draining regime. So here we're modeling our polymer. So each monomer is some solid sphere, and it drags or it interacts with some solvent. And if you zoom out, as we kind of see here, so this is kind of each monomer unit is composed of a solid sphere. If we zoom out, it's just basically, in the non-draining regime, we have a polymer that's highly coiled, really, really compact, with a bunch of monomers that are effectively acting as a single large sphere with some radius, Rs or RH, some hydrodynamic radius, which again scales with your Rg, which scales with your root mean squared end-to-end distance. So it's proportional. Again, we don't care about those, prefactors. So it's going to approximate the radius of gyration. So each monomer is going to affect the fluid flow and the frictional force around the other monomers. So because they're so tightly compact, you could think of like a sphere here, and then a sphere like right behind it, right? So the fluid flow is flowing here. This is going to kind of shield this monomer that's right behind it. The flow is going here, it's going to go around, and it's not even going to interact or touch that monomer unit because we're so highly compact. So there's going to be kind of some shielding where fluid is not going to interact with every monomer unit. So it will, that's essentially what we're saying here. The overall friction is going to be lower than for just if the, obviously if the fluid interacts with every single monomer. So the monomers can affect, are basically shielding their neighboring monomers from the fluid flow effects. So hydrodynamic interactions, and thus, if we're interacting with less fluid, we should expect, again, kind of less viscosity, right? So the viscosity is going to scale with how much, again, our viscous drag is this equation here with V. Our friction factor is kind of telling us, or should scale appropriately with our kind of viscosity here. So if we have more friction, we should have more viscosity. The friction depends on how much fluid is interacting with our solid. So that's kind of the physical picture that you're dealing with here. So this model, the non-draining, is accurate for very, very highly coiled polymers. So, pore solvent, really even theta solvents as well. And so anything that's highly coiled, and fluid flow is highly perturbed from the monomers. Again, we talked about that last time. It's basically blocking. You could treat it as a solid sphere. So if we could treat it as a solid sphere with some approximate size of our hydrodynamic radius, we know that our RH scales with, as you can kind of see here, with our Rg. And if we're assuming theta solvent, again, ideal solution, you can kind of treat it effectively. Again, it'll change a little bit depending on what the conditions that you're in. But even a pore solvent, theta solvent, you can approximate that that radius of gyration as your basically r squared to the 1/2, and we know that that scales as n to the 1/2. So we know that also scales with m. So if we go to the next page, so we know that our friction factor and thus our viscosity is going to scale as n to the 1/2, or from our Florey-Huggins notes, x2 to the 1/2. So we're just replacing the radius of the sphere with the hydrodynamic radius, approximate it as RMSD with some factor. Again, we saw in the notes for an ideal chain it was 1/6. So our Rg was equal to 1/6 r to the 1/2, or r squared, excuse me. R squared and 1/2 over, excuse me, right there for our theta solvent. So we can approximate it with some constant prefactor, and you'll see, again, depends on the scaling factor, but it could be, again, in a good solvent, a bad solvent. So it'd be 1/2 for theta solvent, it'd be 1/3, obviously, for a bad solvent. And even for, this can hold, unless it's, this non-draining case can sometimes hold even if it's in a good solvent, especially if it's not a really, 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 really good solvent. So, but again, this is just more for kind of the scaling, depending on, the key factor here is just going to scale as r squared to the 1/2. So non-draining case, good for bad solvents, good for theta solvents, and then okay solvents as well. And we're going to talk about next time When we're talking about the freely draining case, we're talking about a really extreme kind of scenario where either the polymer is being under high, is in a really good solvent, or it is being kind of perturbed by some really high shear stresses or shear flows. So we'll talk about that next time and give an example of von Willebrand factor. So I will see you all next time. Let me know if you have any questions, and freely draining case next time. Thanks. Bye.